Yeah, welcome to this week's Fireside Chat. We're going to talk a little bit about Typeshare and how we share types between Rust and other languages. So take it away, Jarek.
Yeah, thanks, Ricky. Hi, my name is Jarek, and I'm a developer here at 1Password. And I'm here today to talk to you about Typeshare. Before I get into what Typeshare is and what it does, we have a problem statement. And that problem statement is FFI is hard. So FFI, foreign function interface, is a term broadly used to refer to the process involved in sharing code among multiple different languages. So for instance, let's say you're a company like 1Password, and you've decided that you want to write a core shared component library that gets used across various clients. And you want to write that library in Rust. And then you want your client libraries to call into that core library and make use of those shared components so that you can provide a consistent, fast, cohesive experience across all your clients. Well, you've just now run into FFI, which, as we said here, is a hard problem. And there are many different approaches and tools and things that people have tried out and taken and built over the years to make FFI easier and more automated and safer. And before we get into Typeshare, I want to talk just briefly about what some of these other approaches are and what kind of tools are out there. So the first tool we're going to look at here is called cbindgen, and it is a Rust tool and library to take a Rust C-like API. So you write a Rust lib, and you write a very C-friendly exposed API. So for instance, wrapper C instructs and extern C functions. And then cbindgen is going to come in and generate a C header based on that Rust API that you've defined. And that automated C header that you generated can then be included and used from a language like C or C++, or even a language like Swift, where Swift will actually take the C header that cbindgen outputs and generate some corresponding code for you on the Swift side so that you can work with it a little bit easier. And so that's a nice approach. It takes away some of the burden of automating the really boring part of writing a corresponding header for your Rust C API. But it's still very low level in that if you want nice code to work with on the Swift side, you have to write your own code there and some boilerplate to make things nicer. And you're still dealing with raw pointers and manual memory, and you can still have memory safety issues. And so it's a low-level approach and one that has a specific use case. Then the next tool that we'll look at is called CXX. And this is a tool that dTolney has been working on lately that provides a safe FFI bridge between Rust and C++. And one of the key things about CXX, as it notes down here, is that the resulting FFI bridge from CXX operates at zero or negligible overhead. So one of the key things here is if you're using Rust and C++, you likely care quite a bit about performance. And CXX builds a bridge that will be as performant as possible in pretty much all cases. But it's still a pretty low-level tool, and it still involves manual memory, although this does come with the cell that it will keep things safe for you. And we have UniFFI. UniFFI is the first tool that we're looking at here that steps more into how can we share this Rust code among multiple different client languages like Kotlin, Swift, JavaScript, that sort of thing. And so UniFFI is a tool that a team at Mozilla started. And the core premise here is that you describe the API that you want to expose from Rust in terms of a web IDL-like interface definition language. So you define your API, you implement a Rust API that meets that definition, and then you run this tool, UniFFI, and it will generate a bunch of code in these various different client languages and all the necessary things to interop between those languages in Rust. And that is another great approach. It works definitely for their use case and maybe for many others. And it is interesting there. It does come with more overhead. So they talk about in their documents about how they serialize things. And so there's some overhead to how they pass data back and forth, if that is of interest. And then there's another blog post by a team at Mozilla where they actually made use of protocol buffers. And this is where we step into more of the type territory, where we care a little bit less about sharing a bunch of functions back and forth across FFI and more about we have a bunch of types and we need those types to be defined in Rust or some other place. And we need those types to be in sync between Rust and the client libraries. And so protocol buffers, you describe what you want your types to look like. And then protocol buffers has code gen, where it will generate code that you need to work with that data from a variety of different languages. And that can work out well as long as you're okay with paying the serialization costs. And you have an FFI that's very oriented around types. Disadvantages are you're tied to protocol buffers, which if you look around online, protocol buffers have lot of interesting edges and discussion therein. And you can't really easily swap that out for something other than protocol buffers. And then finally, there's even AWS Smithy, which is, if we want to go all the way, a very generic language for defining services and SDKs, which is really just a superset of defining types. And you could envision a really rich code generation tool built around Smithy that would allow you to define types and keep them in sync between different languages. But what if we take a step back and we take a look at this Rust struct that we defined here that has a couple Serde things, Serde rename all, derive serialize, and it has some fields, some types. What if we could go from this simple Rust struct to this TypeScript interface with corresponding field definitions, to this Swift struct with a codable decoration and corresponding initializer and fields, and this Kotlin data class with a serializable annotation, and again, corresponding fields. What would that look like? Well, it turns out that looks like Typeshare, and that's what we've implemented here at 1Password for use in our code base. And that takes us to the Typeshare REPL. So here we see a REPL that I put together that takes the Typeshare core library and puts it into WASM. So we're looking at Typeshare running in WASM in this web page. And on top of that, I've used Vue, a Rust front-end framework, to build a little live updating REPL where we can type in Rust code and we can see the output of Typeshare in, up here we have TypeScript, down here we're gonna have Swift, and over here we're gonna have Kotlin. And I'm gonna use that to demonstrate how Typeshare can help us achieve what I just presented on those slides a couple slides ago. So we're gonna start out with the Typeshare annotation. We're gonna turn off spell check. And we're gonna define my struct. And we're gonna give it field 1, which was a string. And we can immediately see how Typeshare has helped us go from this Rust struct with a simple field that is a string to, like how we talked about, an interface in TypeScript with a corresponding field, a struct definition in Swift with an initializer and a codable decoration so that we can deserialize and serialize here, along with a corresponding field, as well as Kotlin, a data class with the serializable annotation. And we just get this immediately based off this Rust type definition. And we can continue on here with field 2, which is an I32. We can see how when we add a number, Typeshare knows how to map I32 into a number, a floating point type in TypeScript, an actual int32 type in Swift, as well as an int type in Kotlin. And we can go in here and add a third field. We're actually going to make this one an optional U8. And we can see, again, we're mapping to the correct integer type in all 3 languages, but we're also mapping the optional over. And we can see that we have an optional field 3 in TypeScript, an optional field 3 in Swift, and an optional field 3 in Kotlin. And we can do more here. So we're going to throw derive serialize on the struct, because if we were to want to serialize this from Rust to be able to send it over, we have all the necessary things in Swift. We have codable to deserialize. We have serializable to deserialize in Kotlin. And in TypeScript, JSON is all friendly and at home there, so we don't need to do anything special. But on the Rust side, we actually lean on Serde to do serialization and send these things to the client libraries into this code that we've generated. And that gives us the powerful ability to swap out for any serialization protocol that might work best. So today in our libraries, in our code base, we rely on JSON, and we found that to be perfectly performant for our needs. But let's say we were to find that we have a performance bottleneck on Kotlin on Android, and we really need this other different serialization protocol there to improve performance. We can easily swap that out with Serde and make use of some of the rich Serde libraries that are available on Crits.io. So that's one great advantage and part of the flexibility of Typeshare. And then part of the Serde integration is that we can actually respect Serde attributes. So I can come in here and do a Serde rename all. And we can say camel case. And you can see how immediately I see the camel case rename that's been applied to Serde is also been applied to the generated types. And if we actually go back and forth here, you can see that happen live. And so that's some of the tools that we have available for structs. And we can also define enums. So if I go in here and define a little enum type, we can take a look at what Typeshare supports there. We, of course, support simple variants. So just an enum with a variant, we generate the corresponding definition in Swift, TypeScript, and Kotlin here. But we can do more. We can make use of Rust's powerful data bearing variants. Let's say I want a tuple variant with a string. Now, this actually isn't going to generate anything yet because it turns out that we need to provide a little bit more information to Typeshare in this case. So let's do that now. We're going to need to specify tag and content via Serde. And then we're going to see generated output. And that's because in order to properly share data with these other languages, we need a specific serialization format with where we actually have the type specified by the type field and content in the content field. And you can see how here we've mapped this enum over in the case of TypeScript into a sum type where we've defined different types based on the names of the variants in Rust. And then they have their associated content. So in the case of the variant, enum variant, it has no data, so undefined content. And for this data bearing variants variant, we actually have a string associated with it. And similar for the other languages. Note how for Swift, Codable doesn't take care of quite as much as something like Serde does. So we actually have to generate a bunch of handwritten serialization code here, and Typeshare takes care of that for us. So we can continue to serialize back and forth as needed. And then finally, recently we added support for anonymous structs, where Rust actually gives you the ability to specify anonymous struct data inline in an enum. So we can actually have named fields as part of this enum variant. And we're going to generate, in the case of TypeScript, we just insert a nice property structure there with a field, a named field. And in the case of something like Swift, we actually output an additional inner type that we generate as part of the Typeshare process that isn't explicitly defined in Rust, but we define in order to make serialization continue to work in the presence of anonymous structs. And so this is some of the power of Typeshare. We have these structs defined here in the Rust input, and we have TypeScript, Kotlin, and Swift output. It's going to be kept in sync. It is easy to change. You just change the Rust definition and rerun Typeshare. And you can imagine in a system like what we have within our code base, where we heavily rely on a request response architecture, where client code bases make a request, they get a response back. You have a minimal FFI function layer, which is just what's needed to facilitate requests and responses. And then the actual data going back and forth is all defined in terms of enums. Those enums are type shared, and then client code bases just know how to make requests and responses with well-formed static types. And so that's going to be all for the REPL for now. We may come back here later, but next up, we're going to go dive into the code base a little bit and go on a bit of a tour of how Typeshare operates. So Typeshare is split up into a CLI tool and a core library, and this is the CLI tool. And the CLI tool is actually really small. It exists to do mainly two things. One of those is we use the ignore crate, which is the same crate that stuff like ripgrep depends on to be able to traverse directories recursively and respect stuff like git ignore. And we use that to start off at a root and descend into the directory and find all the Rust files so that we can parse them. And so we take care of that here. And then once we go through all these files, we use Rayon and actually in parallel, go ahead and load all that data and parse it. And when parsing with Typeshare, we construct sort of a simplified AST of the Rust source that gives us the right amount of data that we need to properly output generated types. And we do this all in parallel. And so it turns out that the CLI tool and this approach is very, very fast. And so on my machine in our internal code base, which has about 1,200 Rust files, over 250,000 lines of Rust code, we're able to process all of that and generate output types in about 3 seconds, which is really, really great for our internal workflow. And once we get done with all the parsing in parallel, we generate the types and we go ahead and take care of some formatting business and writing the output if something has changed. So that's all the CLI tool does. So we can dive into the actual core implementation, which, as you just saw in the REPL, compiles for WASM. And there are two stages here in the core library. One of them is parsing, which is mainly driven by this parse function, which takes Rust source input as a string and returns parse data, which is structs, enums, and aliases that come from the Rust source. And a fun little tidbit here, we actually make sure the input string contains Typeshare before we do any processing, because it turns out we use Syn to parse the Rust source code. And it turns out that making sure that there's actually something that we might need to handle there first is a nice performance win. So we do that. And then, yeah, we just parse the file with Syn and we go through all the items we find. And if they have the Typeshare attribute, so that attribute that we wrote in the REPL earlier, we make sure that we parse those out and we hold on to them for later type generation. And so we can see here, we do some sort of rename all handling and stuff like that. So we actually have this get ident call, which gets an ident for a Rust type, like a struct or an enum, and we make sure to keep track of both the original name and whatever the rename name is coming from sort and stuff like that. So we can generate an appropriate name in the output type side. And we have code to handle enums. We handle various different enums unnamed with named fields, as well as type aliases and stuff like that. So parsing is really just about constructing something simpler, because the syn AST that they provide is very complicated and it has a lot of stuff in it, and we don't need most of that. So we simplify it down quite a bit before we actually get to type generation. So we move into the type generation phase, and that mainly revolves around this trait language. So the language trait defines a couple different functions that implementers need to provide implementations for, such as the ability to write out a type alias or a struct or an enum for your given language. And type generation is a very simple process. It's driven by this very small function that starts the file, writes aliases, structs, and enums, and then ends the file. And so the rest of the magic lives in the language implementation files. And in here, we can take a look at, for instance, the TypeScript definition, which has some code to handle formatting TypeScript code based on prettier if it's available. Code to begin a file with a little simple header for TypeScript. Code to write out a type alias in TypeScript, which is a very simple export type line, and code to handle structs and enums. And a nice little tidbit here is when we're handling enum variants, we may need to write out variants for anonymous structs, like I showed in the REPL earlier. And we actually reuse the write field implementation that is also used for struct definitions. So there's some nice code reuse going on there. We have format type, which is a little function that helps us map from Rust types to TypeScript types, which, as you can see here, so number types, I16, I32, various different numbers, they all map to floating points in TypeScript. And we actually have this special type that we'll talk about in a minute, I54 and U53. So TypeScript has no way of representing something like a U64 because there isn't an integer type with enough precision to represent that on the TypeScript side. And so the most you can get is like an unsigned 53 bits of precision. And we have special handling for some of that, so we can get the most precision out of our numbers in TypeScript. And an implementation of writing comments in TypeScript, which is, yeah. And then Swift. Swift is one of the more complicated ones because, like I showed in the REPL, there's a lot of sort of manual bookkeeping that we need to do to keep track of outputting the special codable stuff. So codable, a little bit less flexible than something like Serde, and in order to support deserializing and serializing the different types properly, we need to generate some code ourselves. So this keeps track of that here. But other than that, it's a very similar process to what we see in TypeScript. And you know, we have implementations of writing a type alias, writing a struct. There's actually handling for decorators. So actually, if we go back to the REPL really quick, I can show this off. We can come in here in the Typeshare attribute and specify Swift equals. And then if you pay attention to the struct definition here in Swift as I type, we can go ahead and specify equatable. And so we can tell from the Rust side, hey, Typeshare, this struct that we're generating should also be decorated with equatable on the Swift side. And that gets handled right here. So we take care of that and writing out the fields and everything, and a very similar process. And then also for Kotlin. And the Kotlin implementation is also one of the shorter ones because serializable is pretty powerful. And so we go ahead and write all that stuff out. And very similar to how we had in TypeScript, we have the ability to map from Rust types into types in Kotlin, which we take care of here. And then finally, a little bit of common code that gets shared between all of them. So like I showed in the REPL, we write out this anonymous struct, an actual struct definition for the anonymous struct that we had in Rust, and that gets taken care of by this function, write types for anonymous structs. So it'll actually take a look at this enum and see that it has an anonymous struct defined as a variant, and it's going to take care of writing out the appropriate struct for that variant based on whatever language implementation we give it. And yeah, so that's a little bit, well, actually, so before I finish talking about Typeshare's implementation, let's go look at the annotation. So this is the actual proc macro, which, as you can see, this is very short right now. The proc macro doesn't do anything, mainly, and that's because we've made the choice to implement Typeshare as a CLI tool that actually parses Rust source and kind of runs on its own. as opposed to implementing Typeshare as a proc macro that then gets invoked by the Rust compiler. And that comes with a set of trade-offs. So some of the nice things, we get really great performance because we are able to parse files in parallel, use Rayon, and we have complete control over how that all works. There's some great flexibility. So if we want to parse Rust files that aren't actually part of the build process, we can do that. It also makes stuff like the REPL possible. This might not be as easy to extract out into a library that could be used in a REPL if we had this working as a proc macro. But it does come with some downsides, and that is namely right now we don't support generating types for types generated in Rust by a macro. So if you write a macro rules macro or a proc macro in Rust and you output a Rust type definition and give it a Typeshare attribute, we're not going to see that today. And that's because we run before macros get expanded. And we could potentially look into solving that with something like cargo expand and expanding the code prior to running Typeshare, but we haven't gotten to that investigation yet. So for now, macro generated types are unsupported. So that's a little bit about the annotation. And then finally, we have this lib here. And this is more sort of runtime stuff that is for our internal code base. And this is also where we define stuff like E53 and I54, which are those integer types I mentioned that let us get the greatest possible precision out of TypeScripts and their number types there. So that's a little bit about how Typeshare is implemented. Now let's talk briefly about how Typeshare is tested. So testing is important for all software, as we know, but it's really important for Typeshare because it can be really easy to make changes to code generation and not realize that they impact other things. And then, oh no, we're generating broken code. So we rely heavily on snapshot testing in Typeshare today. Previously, we had a unit test system, and it was really simple. We just put Rust source strings in the source code and the expected output strings, and it worked all right. It was a little annoying to put together, but once it was there, it worked. But the problem with that is, well, for one, it's difficult to update them. So if you changed, say, spaces to tabs in the output, or you changed the formatting of the output in any way and added new lines, then you'd have to go back through all the source strings and update them manually, and that's not a very fun time. And so we came in here and we rewrote the test suite to be entirely data-driven based on these folders. And each one of these folders contains an input Rust file. And this is the file that is going to be handed to Typeshare, and Typeshare is going to generate an output for. And then the output files for whatever languages you specified should be handled for the test. So here we've said all of Kotlin, Swift, and TypeScript, and we can see the output for this input when Typeshare runs. I can go ahead and invoke this. If I go to a terminal here, we can do a cargo test in the crate. We can see it passes very quickly, 0.02 seconds on my machine. We've run 100 tests, and we've just confirmed that all of these test cases for the given input for the test case, they are generating the exact same output in the current state of Typeshare, which is really great. And let's say I came in here and I don't know, I took this type and I changed the output a little bit. So you can see my editor formatted it. The formatting is different. I removed one of the sum types. Let's see what it has to say now. And we're going to see that it failed. And we actually get to see the content that was expected. We're going to see the actual content Typeshare returned, and we get a little bit of a colored diff between the two. And if I were to decide that I actually want this output, I can go ahead and throw update expect equals 1 and set that environment variable before running the test. And if I go ahead and run that, I can see that Typeshare's run, and it's actually written its output to the file. So I've said, okay, I know that this test is different. It's changed, but that's okay. I want you to go ahead and update that expectation. So you can imagine a case where you change formatting or change tabs to spaces, and we can very quickly, with one command, just update all the test cases, and then you can go ahead and look through them in Git and make sure that the Git diff looks good. You can go ahead and commit that to the repo, and that'll become the new source of truth. Then as far as a little bit about how those are implemented, let's go back to the file here. Most of the implementation is here in this check function, where we take a test name as well as the output name of the file for the like output.kt or output.swift, as well as the language instance, the generator to use. And then we come in here and we take care of loading the input file and generating Typeshare's output. And then we actually use expect test, which is the same library that they use in Rust Analyzer for snapshot tests. We also make use of that here, and it's serving us very well. And to actually generate things to call that function, we have a macro called tests, and it generates a nice simple testing structure that corresponds to the file structure over here. So for each one of these folders, we're going to get a module with the name of the test, which is the name of the folder. And we're going to get, for each output file in here, for each language that we want to have tested, we're going to have a test function generated with the name of the language. And it's going to call check with the appropriate parameters. And what that all amounts to is a very low boilerplate way to describe tests in Typeshare, where you can go ahead and name your test and then specify what languages it should run for. And it even supports passing more specific arguments if you need to configure what happens for that given language in the test. And we can actually go ahead and quickly try adding one here. So if I add my new test, and we're going to have to specify what languages it should run for. So let's say Kotlin, Swift, and TypeScript. Go ahead and save that file. And then I can go ahead and run for the first time. And we're going to see my new test appear over here. And it's given us an input file that we can go ahead and put input in. So let's say struct my struct. And we'll just give it a field. And let's not forget to give it the Typeshare annotation. I'm going to run this again, and we're going to see, so it's actually generating output now. So we can see we're expecting nothing because we have no expectations, but it's returning output because we have given it input. And now we can just tell it, okay, please write that to disk. And in about 10 seconds of work, we've created a test case, we've given it Rust code input, and we've got output written to disk that it's going to be checking against as it runs in the future. So it makes it quick and easy to add tests, maintain tests, update tests, and it's a really great flexible testing system. So that's a little bit about how Typeshare is tested. And that will conclude our tour of the Typeshare code base. So one thing I will mention as we wrap up here is that Typeshare, the flexibility is really great for us. And one of the ways that it's been great is as part of moving our web extension over to Safari, we had various reasons that we needed to move the WASM component that normally runs in WebAssembly in the browser and is written in Rust. We needed to move that out to a native component that ran actually natively in macOS. And because of Typeshare and our request response architecture, we were able to do that very quickly in a matter of days. And we were able to move that WASM component out to a native component and communicate over XPC. And so that was really great for us. Typeshare wants a few things. So we would love to see support for namespacing. Right now, we parse all the Rust types, and we just dump them all into a single file. And that's really great. It's simple, it's straightforward, but it results in a really big file, which isn't great for editor performance. And it also means that if you have two types that have the same name, even if they're in very different places in the Rust code, they're going to conflict in the output. And so we'd really love to see support for namespacing and generating a nice file structure that kind of mirrors what the structure is in Rust. We'd also love to see, as I mentioned earlier, we don't currently support Rust types that are generated by macros. And so we'd love to see support for that, whether that be some sort of proc macro implementation or actually running cargo expand prior to generating types. Build system caching. So right now, Typeshare is very fast, it's parallel, and we rely on that heavily in our internal build system. But for any sort of bigger code base or on slower machines, it would be really great to have caching so that we can understand, okay, these input files haven't changed, we don't need to run Typeshare on them. It'd be great to support more languages. And that's always a great thing. It would make it more useful as we move towards open sourcing this in the future. We'd love to improve the errors. So right now, errors are very simple. There's not a whole lot of error output. It doesn't reference the source code. We'd love to have richer errors that help people identify problems with their Typeshare definitions quicker. And also a simple build.rs API. So right now we have the CLI tool. We invoke it as part of our makefiles in our internal code base. But in the future, as we move to open source this, we'd love to see a simple API to integrate it in small projects where you just want to run it from build.rs and be done. And then there's a couple things Typeshare needs before we ideally would open source this. And so documentation is one of those. We should have some good documentation so people have a nice thing to reference as they're working with Typeshare. A small example code base would go hand in hand with that and give people something to jump into and play around with and see in practice. Improved snapshot testing. So right now I showed off some of the snapshot testing and how it works. And it works great, but the problem is there's no guarantee that the snapshots of code actually compile. So you could be adding a new feature, adding a new test, and you write some Rust code, you implement something in Typeshare, and you look at the generated output in the test, it looks good, you check it into the repo, and then you find out that as you actually try to use that feature in a live compiling code base, it doesn't actually generate valid code. And so what we'd love to see is continuous integration that actually runs the compilers for various languages on those snapshots and make sure that the snapshots are actually valid compilable snippets of code. We'd like to see some more user configurability. So there are still a couple hard-coded things that we need internally for our types. And we'd love to pull those out into user configurable things that could work for anyone using the code base. And finally, we need contributors because, well, everyone always needs contributors. So we'd love to get some people helping out, more people pitching in. We'd love to see support for more languages, like I said earlier. And with that, thank you. That will conclude the talk about Typeshare. And at this point, I'm happy to take any questions from anyone who has any.